Hello, I am Sedat Kömürcü. I am a researcher from Istanbul Technical University. I hope everyone is fine in these pandemic conditions. I am here to talk about a nonlinear investigation of the short column effect for confined walls under cyclic loading. The content of the presentation will be the purpose of the study, modeling of masonry walls, finite element analysis of confined masonry wall models, and I will conclude with some recommendations. The purpose of this study to explain the continuous micromodeling for masonry walls, to understand the structure of contact and target finite elements, to analyze short column effect of confined masonry walls. This short column effect, this is really important effect for to analyze the structures. This effect is, you can see this effect, this schematical description of this effect. There are some shear cracks in the structures, and this is the real example of the short column effects. And you can see the the very damage of these effects. The modeling of masonry walls, there are some modeling techniques. You can see here, I will use the continuous micromodeling strategies. In this strategy, there are some masonry units and mortars, and there is any interfaces between the masonry units. And the other strategies are the detailed micromodeling, simplified micromodeling, and the macromodeling. In this study, there are some confined masonry wall models here. You can see this model, and this is a 1 dimension, 1 meters and 1 meters dimensions, and a confined frame is placed around the wall. The material properties in this study are the modulus of elasticity and Poisson ratio for elastic uh, material properties, and for the nonlinear materials, the Drucker-Prager fader surfaces are is used in this study, and for this material properties are the friction angle and the rotation angle, and these values for the friction angle is 60 degree, and the cohesion is the other parameters for the Drucker-Prager failure surfaces. It is 0.35 megapascal, and this in this study, in the cyclic loading, you can see this formula. It is applied for the wall models, and in this formula, A is the amplitude and the W is the frequency and T is the time. And there are the amplitudes for the loading steps 0.5, 1, and 1.5. And the loading parameter speeds are constant during the experiment. And the period of the study you can see here. And the Drucker-Prager failure surfaces can be represented by this formula. The sigma values are the principal stresses, and these values represent the compression strength and the tensile strength of structures. And in this study, for the finite element analysis, the solid 65 element is used, and this is really a good element for bricks or concrete structures. For the target and contact elements, the uh, between the masonry wall and frame. These elements can be shown here, and the stiffness parameters between this and the normal and shear. And these are can be calculated from this study. The confined walls here at the a confined wall with fully infilled, and B and C, you can see the 2/3 and 1/3 of the confined masonry wall, and at the D, you can see the empty frame. The minimum stress is really a significant factor to understand structural behavior of the walls. It's significant. Uh, the minimum principal stress distribution on the wall are shown here. It can be seen from the principal stress distribution. There is a compression toe at the bottom left corner of the frame wall system, and the short column effect starts for 2/3 and 1/3 masonry infill ratio wall at the interaction point of the upper right and left corner of the wall of the frame. There are short the short column effect starts, and the highest stress body is produced at these points shown in figure B and C. The minimum principal stress is shown at the empty frame here. It's seen that the highest stress occur at the corner points of the frame. It must be noticed that these stress values are belonging to the different stage of the experiment. The principal strain distributions here, and you can see the uh, failure mechanism is occurs as a diagonal line from the bottom left corner to the upper right corner of the frame system, and it can be seen from two diagonal cracks which occur at the later stage of the experiment in terms of cyclic loadings. It can be seen from the figure B and C. When the infill ratio decreases, the short column effect appears. The black points at the both upper corners of the masonry wall, the upper corners of the frame show the location of the plastic hinges here. And due to the short column effect, the confined masonry walls having 2/3 and 1/3 infill ratio, failure of the system occur at the interaction point of the frame and the masonry wall system. Here you can see the load deflection curves of the experiment. It's seen the confined wall models has much more strength than unconfined wall models. The walls which produce short column effect has very low strength here. It can be noticed that there is a huge difference between the fully infilled masonry wall and 2/3 and 1/3 infilled masonry wall system. You can see the graph about the cyclic loading. It's clearly understand from the figure that the confined frame has much more strength when it contains full of infill material. And here, 1/3 of the masonry infill wall and empty frame figure here. Empty frame has more ductile than the masonry wall with 1/3 infill wall, but 1/3 infill wall has much more strength than the empty frame. The conclusions, the modeling technique, the material model, and the fracture hypothesis form a combination for masonry modeling. In continuous modeling technique, and behavioral masonry structures can be modeled without using interfaces. The structural behavior of a confined wall is dramatically changing in terms of infill frame ratio. The short column effect is a very significant factor to determine the strength of the structures. Thank you very much for your listening. I will be very happy to hear from you for your questions or advices or the working invitations for about the modeling of structures. Thank you very much.